only got 24 students in that class, 26, I think. So it's confusing. Okay, so if you're just joining us, we're taking a look at problem number 2, was it? Just a minute, let me pull this up again. Number 3. Yeah, so it's number 3, and in particular, we're going to do the Simpson's rule and the error. So let's see if I can whip this off really quick here. And we're supposed to do this for 2 and 100 subintervals. And they want us to do this particular integral. Let's just do the integral by hand. Sorry, I'll pull this up here. So let me just do the integral by hand. I know I could use Python to do it, but I'm going to do it by hand. 2 to 6 of x squared minus x dx. Okay, so it's going to be x cubed over 3 minus x squared over 2, evaluated from 2 to 6. So it's 216 over 3 minus 36 over 2 minus 8/3 minus 4/2. Okay, so what is this going to be? 216 minus 8 is 208. And then let's see, 30, I guess that's just 18, and this minus 18 plus 2. So whatever that is, I guess I should just get the decimal here. I was hoping it would come out to be a nice integer, but it is not. So 208 over 3 minus 18 plus 2. So I've got 53.33. All right, so there it is. So that's the actual value. I guess I could write it as, just a minute, math, 160 thirds. So we'll use that in Python. So bear with me for just a sec. I'll switch over. I know I'm sitting super low here. I don't know why this seat won't get any higher. So here is the Python code that we were using before. I've kind of I've reorganized it a bit. So let me just recompile everything. Let's see, here we go. Just so that I could have all of my rules in one place. So we've got all the basic trapezoid midpoint Simpson's rule in one block. And I've got the composite rules down here. So there they are. And then let's add a code block down here. So basically they just want us to, oh, here, just a minute. Let's do this. Let's call this A. A is equal to 160 thirds. Okay, that's better. Okay, so we're going to do this. Print. We're going to do the composite. Oh, I need my function to be defined. Sorry, let's go up here. I thought I turned off those little so-called help menus. So let me just put my function. So this is going to be return x times x minus 1, was it? What was that function? Yeah, x squared minus x. So there's that. I guess I have to recompile that so that it'll be in there. Okay. Now that I've got that, let's go ahead and crank this out. We're going to do the composite Simpson's rule. And the function, and we're going from 2 to 6. And 2, I believe it's 2, right? Okay, so there's that. And then we're going to do this minus a. I'm sure I could do this more efficiently. Let's just see what happens. Okay, so we're pretty darn close, actually. Wow, actually, we're right on the nose. Yeah, composite Simpson's rule. Oh, it makes sense. I don't even know why I've had you do this one. It's because I wasn't looking closely enough at the functions. This is a quadratic function, so Simpson's rule is going to do exactly. It's going to give you an exact value. So this particular one, it would be much more interesting to do this with the sine curve or the cubic from number. Did you have to do 6.2 with Simpson's rule? Okay, yeah. So that would have been much more interesting, is the cubic. But this one, it's going to be exact because, yeah, I don't know why it didn't hit me when I was doing this. Yeah, so this one is exact because it is because the way that Simpson's rule works is why is this not moving? Here we go. Is it interpolates with a degree 2 polynomial, and you're interpolating a degree 2 polynomial with a degree 2 polynomial, so you're going to get an exact value. So that was kind of boring, actually. Wow, that was a lot of work for absolutely nothing. I should have recognized that the moment that I did this up here. So sorry about that. I don't know if that even comes close to answer. Was that the issue? That was the issue, is that it was exact? Yeah, yeah. So it was more interesting when you did the midpoint rule and the trapezoid rule. Yeah, there's nothing to do. Sorry about that. All right, anything else that was particularly interesting or question about? All right, well, let's do this little exercise. I have it says quiz at the top, but I think it's a good exercise to do just because I don't know what you did on Monday, to be honest. I mean, I made my videos and I was like, oh, I hope they do something. But this is a little bit of a rehash of what we did, what you were supposed to do for Monday. Plus, I've thrown Simpson's rule at the bottom so that you can compare the three. So I'll put this up on the screen in a minute for those watching from home. But let me give you this. And so what I'd like to do is to try this as a sort of a, pretend it's a quiz, and then we'll go over it to see how closely you're understanding. I think there's an extra one you can give someone. There's two, maybe not. There's not an extra one. There you go. Oh, there is an extra one. There you go. Good job. All right. So when you get sick of trying to do this on your own, you can always compare with your friend next to you, because, like I said, we're going to pretend it's a quiz just for a bit, but then we'll go over this so that you have something to take with you. Not that. There it is. As you're finishing things up, I want to point out that on these graphs, I'm hoping that you'll sketch like kind of like what we did in class with the rectangles or the trapezoids. Just show me what it is that you're actually doing with these things. So even if you can't remember the formula, especially for Simpson's rule, maybe you can draw something pretty. We'll see what it looks like. So I'll give you about a minute or so more, and then we'll go over the answers. All right, let's see how you compare with what I have. So we'll start off with this first one, the midpoint rule. Midpoint, of course, you're going to take the midpoint of the interval, and that's going to dictate how tall your rectangle is. And so I was kind of hoping you would draw something sort of like this. There, I don't know if you shaded it or not, but that's what I'm interested in, is this area as an approximation for the integral, the stuff above, or below the curve, rather. So we just need to know how tall that is. And of course, that's going to be the function value at 2. So f of 2, which equals 1. You can plug 2 into this function that I have there. I left you a huge amount of space. I don't know why I did that. So the final answer there is that the area is going to be 1 times 4, which is 4. Does that look all right? So one midpoint. Okay, so one trapezoid. Of course, if you were going to do a composite midpoint, you'd chunk this up a little bit more, but we'll just see what one looks like. Now let's do one trapezoid. There we go. I was kind of hoping you'd do something like that, so that you have the two end points of that interval. And this f of 0 happens to be 1. Can't do 2 to the 0 is 1. Very good. And then here, this f of 4, I believe, is 2. Isn't that right? Let's see. 2 to the 4th is 16. 4 squared is 16. Yeah, 2. So now we just use the 1/2 times 1 plus 2 times 4. So what's that? 3/2 times 4, which is 6. Makes sense that it would be bigger than the last one because, of course, you're tilting upward like this. And I think you probably have a feel, just looking at the picture, that this is a worse approximation for the area than the first one. The first one, you can see that the area that we are omitting, these two, are not too far off from the area that we're adding in. So you're adding in this area and omitting those two areas that are above that line. Let's see how we contrast this with Simpson's rule. So Simpson's rule, you take 3 points. And so here, I don't know if you remembered the exact formula, but hopefully you remember the process. Is you have 3 points now, and we're connecting those 3 points with a parabola. I don't know if that's exactly what that parabola would look like, but I'm going to go with that. And that's the area that I'm shading. This one's going to be a little harder to compute, but there's a nice formula for it. So we do h times, you've got f of a plus 4 times f of the midpoint. I'll just put m there, plus f of b all over 6. So it's this weighted average, if you will, of the 3 points. And this comes directly from, I don't know if you watched the video, I guess I didn't really, I don't know if I went over it or not, but this comes directly from integrating the interpolating polynomial of degree 2 through those 3 points. You would get exactly this formula. Anyway, here h is 4. F of a was 1. We did that one before. 4 times f of b is also 1, plus f of m is 1, the midpoint. And then f of b was 2. That all divided by 6. And so this is going to be 4 times, what is that, 7/6? So, hold on a sec. Okay, so 28/6, but divide that by 2, so 14/3. 4.66. Does that look all right? So presumably this one's going to be the closest, although I don't know that I trust Simpson's or any of these rules, to be honest. I don't trust them very much with a single iteration because so much could go on. The business with Simpson's rule being more accurate, what that is referring to is the idea that the more, like you're going to get closer quicker if you break this up into more rectangles, or in this case, more Simpson's rules. All right, so hopefully you were able to remember those, and whenever we have our next test, you'll have something like that. So I'd like to have practice so that you know what to expect. Okay, so today, what are we doing? We're going to be taking a look at specifically how quickly things converge. So it's this slide in particular. And I want to do a little bit of experimentation with this. So it's these three up here. We don't care so much about the 3/8 rule, but Simpson's rule, trapezoid rule, midpoint rule. How quickly can these converge, and how can we implement this efficiently? Because what I've done, at least the way I've shown you, not efficient, not at all efficient. So I want to try to come up with a better way to do this. So let's see, where should we start with this? First off, let me point something out about these formulas over here. This we have no control over. I don't know what C is. I don't know what I compute the second derivative, but I'm not going to know that. The one thing on this that I have control over is H right there. In particular, the way that I would have control over H is that H is B minus A over N. The reason why I'm pointing this out is that each one of these is going to be related to a particular sequence. And these two, both of these, are on the order of 1 over n squared, 1 over n squared. And the reason for that is that you have an h squared, and so you're going to converge to your root, or not your root, to your approximation on the order of 1 over n squared, meaning that if you want to get, you'll get closer to it, similar to that sequence, as you add more subintervals. So these two down here, but in particular Simpson's rule, is on the order of 1 over n to the 4th because of that h to the 4th, and it's because h is b minus a over n. So this is much faster. So that's what we want to explore today. So let's go and grab this. So let's see. First of all, I'll put this down as midpoint is on the order of 1 over n squared, and Simpson is on the order of 1 over n to the 4th. So with this in mind, let's see if we can predict how many iterations we're going to need to get to a certain, how close we're going to get based on some stuff. So let's go back to the problem up here. So the one on your quiz, or this sort of quiz, this one right here. I want to know how many iterations do I need to make? How many times, like, how many subintervals? What should n be to guarantee that I'm going to be, can I predict that sort of thing? So let me rewrite that integral down here. 0 to 4, 2 to the x minus x to the second plus x over 2. So I suppose that before we go any further, we need to actually figure out the exact value of this. So take a minute, see if you can remember your antiderivatives. This one's not terrible, but I'll help you out, don't worry. So take a minute though, see if you can remember your antiderivatives for this, then we'll do it together. Let's see. This will give me a chance to see. That's all right. Yeah, I figured that would be the sticking point. Let me do attendance so I can do a randomizer, and then I can ask one of you. Yeah, give me a sec. Here, this is more fun. I figured that would be the case. Okay, finally. Sorry it took so long to do that. That's good. All right, random. Oh, here we are. Okay, so we have 3 different functions here, right? 2 to the x, x squared, and x over 2. Sam, which of those do you want to do the antiderivative for? Okay, what's the antiderivative for negative x squared? Beautiful, good job. Okay, so that's one of the 3. Let's get the other 2. All right, Briar, do you have a choice? Which one would you like to do? All right, very nice. And of course, we're going to be evaluating this from 0 to 4. Oh, what in the world? 2 to the x. Okay, I'll make it a little bit easier on you. Eli, do you know what the antiderivative of e to the x is? To the x? Yeah, e to the x. It's one of our favorite, right? Favorite integrals is e to the x is its own antiderivative. Same thing with its own derivative. So 2 to the x is almost the same. It's very similar. The only difference is that instead of having just 2 to the x, you have 2 to the x over the natural log of 2. So that's, yeah, you knew that there was going to be some trick like that. But I mean, one way to remember this, if you ever are in an emergency situation and you need to know 2 to the x, the derivative of 2 to the x or the integral, what you could do is you could remember that 2 to the x is e to the natural log of 2 to the x, which is e to the natural log of 2x. So then you could use substitution or whatever. Because that, like for example, the derivative of 2 to the x will be natural log of 2 times e to the natural log of 2x. So you end up with an extra factor of natural log of 2. Okay, but getting back, I know I digress. So let's actually find the actual value of this. This is going to be 16 over the natural log of 2 that we all know is what, 0.69 or something. And then this will be x cubed is 64 thirds plus x squared is going to be 16 over 4 is just 4. So that's going to be the top limit. And then the bottom limit is just 1 over natural log of 2. Is that right? Because all the others are going to be 0, 0. All right, I'm going to have to use my calculator at this point so that we can get, I mean, we could just write it down. I guess that's going to be 15 over natural log of 2. There, 15 over natural log of 2 minus, what's that, 12, 52 thirds. I think that's what it is. But let's get a decimal equivalent, so we got a feel for how close we are. 15 over the natural log of 2. And we're going to subtract off 52 divided by 3, and I got 4.30709. Good enough. Okay, I need to go remind my, oh, actually I don't. I remember. the midpoint rule was 4. So midpoint rule, I was off by 0.307. Simpson's rule, Simpson, SIPMs, just a minute. Simpson was 4.667. And so I was off by actually a little bit more. So the error here was 0.307. And here the error is equal to 0.367. The error just being the difference between, oh no, it's 360. Sorry, is that better? Well, there it is. So it's the difference between the truth and the, so this is an absolute error is what I'm doing here. Okay, so like I said, I want to try to figure out how quickly am I going to get to the truth? So midpoint, the error will decrease on the order of n squared, and the Simpson's rule will decrease, get smaller, on the order of n to the 4th. So if this is the error we're starting out with, then let's take a look and see what happens if we double. So now I don't want to do this by hand. I'd much rather do this on in Python, and I'd rather not have it take up the whole screen. There we go. Okay. And now I can't see my errors. Of course, it's on the wrong side of the screen. Just a minute. There. Good enough. And I'm going to do this here. Okay, so let's do a little bit more experimentation. So give me a sec while I get this pulled up so I can see everything that I need to. Okay. Where is it? Okay, so we're right here, and let's get rid of this. So this is going to be 15 divided by the natural log of 2. And I know it looks like I just typed log of 2, but it's actually in Python, that's the way you say natural log, minus 52 divided by 3, was it? Sorry, it's behind the Python is where it is on the, it's on my iPad. Okay, so that's going to be the target. Oh, and I need to have our function. Give me a sec here. So I guess I might as well just keep going. So, whoops. There. Every time I make a new function, I just, okay, return 2 to the x minus x to the 2 plus x over 2. That was the function that we had. I need to get that into the memory. So every time you change something in one of these blocks, you should rerun that block so that it has it in its memory or whatever. And now we can go down here and we're going to do the composite Simpson's rule between 0 and 4. You know what? This is so inefficient. Let's do it this way. So we're going to say that B is equal to the composite Simpsons with F between 0 and 4 with 1 interval. Give me a sec. C is the composite midpoint. I know this feels super inefficient. I think I need to put a capital S up here. Midpoint. Oh, do I have that spelled right? Composite trapezoid. Oh, mid P. Yeah, I've got it right. F, 0, 4, and 1. And then we're going to just print these things out. So this is the work we've already done. Not very exciting, but I just wanted to make sure we had the baseline here so that we have, first of all, composite Simpsons, and then the error from the composite Simpsons, which is B minus A. And then we'll do the composite midpoint, and then the error from the composite midpoint. And let's run that, and it says it's got a problem. Oh, too many parentheses. I got too excited. Okay, so there it is. So this is exactly, is that right? 4.6. Yep, that's what we had. And this is the error. Oh, I have 0.360. This is 0.359, close enough. And then this, of course, is what we got for the midpoint rule. And then that's the, I should use the absolute value, shouldn't I? Let's change this to absolute value, ABS of this stuff. Okay. That really annoys me that that shows up there. I thought I got this to shut up. Just a minute. If I go up here, just a minute, editor. I thought I shut something down. Maybe that? No? Huh. I don't know. I thought that I had shut something off and had gotten rid of the annoying thing. I'll just cancel that. I'll just have to deal with it. It's okay. So there it is. So absolute values, that's better. Yeah, now you have the absolute value. Okay, so what we want to do is we want to compare this with, I guess we're just going to have to crank this through again, copy and paste. And so find out what happens when we do 2 of each of these. So let's go ahead and do that. Okay, so you can see that when you, wow, really? Just a minute. That really seems unusual to me. That the midpoint, you see, I don't know if you're looking what I'm looking at. Let me make this bigger. I think I'm done with the iPad for now. So pull this over here and we can all see a little bit better. Yeah, I don't know if you see, like here, let me navigate for you here. This is composite Simpsons with 1 Simpson rule. Here's 2 Simpsons rules. Here's the difference in the error. This is 1 midpoint. This is 2 midpoints. So it's just weird. I mean, geometrically, it must, let me just go up here and look at the geometry of this. Oh, I see what happened. Yes. Yes, I see. So if you're looking at your piece of paper, if you were to draw 2 midpoints, you can see that the 2 midpoints, one of them is up and the other one is down by the exact same amount. You can kind of see how that would work. That's kind of interesting. Okay, but anyway, that's not really all that important. The important thing is I want to estimate how quickly I'm going to get to the truth. So let's do one more. If you'll bear with me, let's do one more. Copy this and go for one more of these. And now I'm going to do 4. There it is. Okay. Okay, now at least the composite midpoint is getting better. Okay, so this is 1 Simpson, 2 Simpsons, 4 Simpsons. 1 midpoint, 2 midpoints, 1, 2, and then 4 midpoints. So it's getting closer, but it's going pretty slowly. So here's what we can say though, is that when you double, so if you compare these, when you double the number of midpoints, it looks like we've gone from 0.3 to 0.09, which is you've reduced by about a factor of 1/3, would you say? So about 1/3. Whereas here, when you double the number of Simpson's rule, we've gone with a factor of, let's see, 26 and 7. I might have to actually do this on my calculator. How many times does 17 go into 260? About 6%. So this is about 33%, a little bit less, 30% maybe. So your error here is about 30% of this. Here it's about 6%. So the whole business with the on the order of n squared, that's this one, as opposed to n to the 4th, is that this error will continue to decrease at a rate that's pretty predictable in the sense that, let's see, you're going on the order of n squared. So we just went from, well, let's go from 1 to 4. From 1 to 4, let's see, it'd probably be easier if we have number of digits. So let's see, 1 over into the second to the 4th. So 1 over into the 4th, you have 1/16. is what you should expect. Whereas here, yeah, when you double, you should expect about 1/4 because you're doubling. So you have 1 over n squared. And that's a little bit less than 1, or not as good as 1/4, but it's about 1/4. Here you should expect about 1/16. And in fact, it is about 1/16. So we could use this to predict how much closer we're going to get. Like if we needed to get to within 0.001, let's go ahead and write this down. Just a minute. Sorry. Put this there. Okay. So let's start with, let's say that our target, or the tolerance is I want to be within 0.0001. How many times? How many? Now bear in mind that the midpoint rule is on the order of 1 over n squared. Simpson's rule is on the order of 1 over n to the 4th. And we've got a little bit of data now. We know that for the midpoint rule, 4 midpoints got us to within, whoops, it's gone. There we go. So let's see, I want to just see how well you can do this. Got us to, where's my answer? Oh, there it is. 0.90, sorry, can't see it on this screen. There. Oh, now it's too high, of course. There. 0.09. I'm going to write this down. 388. Good enough. And then for Simpsons, got us to within 0.00171. 0.00171. Okay, so let's get back to this. So here's your challenge. I want to know how many you're going to need to get within this. So see if you can work it out, maybe with a friend if you'd like. But the key here is that when we say that we're on the order of 1 over n squared, what I mean is that it's predictable in the sense that you're going to have your error is going to equal to some number times 1 over n squared. And same thing here, the error will equal some number. I don't know what number it is. Well, I should say it's less than or equal to, but these are pretty close to being exact here. So these are going to be predictions. They're not going to be perfect, but so you're going to, in other words, here's what I would suggest you do is try to figure out what the K is or whatever this constant is, and then go from there to figure out how big of an n do you need in order to ensure that your error will be within 0.0001. You're almost there with Simpson's rule, so not far. I probably should have put another 0 up there. But yeah, take a minute, see if you can work it out, and then we'll come together and try it. All right, curious to see where we are on this. So like I suggested, I mean, one way to go about this is let's figure out what this k is. Maybe I should have named these different things. This could be k sub m for midpoint, k sub s for Simpson's rule. I really need to stop using this particular color, don't I? It's not the best. Let me see if I can just change it up here. There we go. I'll change it to something maybe darker. How about this? Is this one better? S? That's more annoying. Okay, well, I'll try to work it out. That should be good. Oh yeah, for you gamers, this reminds me of the a game that my son-in-law bought over Christmas called Hues and Cues. It's like it's a party game where you're trying to guess colors. You got this big board that looks like you can't see it, but I'm picking all the custom. You've seen it? Okay, yeah. It seems kind of cool. So yeah, you need to buy that and bring it, or maybe I should buy it. I don't know. Oh, you have it? Oh, bring it. Oh, that'd be super exciting. Okay, this is better. This green. Okay, whatever. Okay, so what about the Ks? So for the midpoint, and this is, of course, notice that the error is less than or equal to some. That's what the big O means, is that it's error. Your error will always be less than or equal to some constant times this thing. So, it might not be it's not going to be exact, but it's going to be approximate. So, but we're approximating. It's okay to approximate. So what did you get for your K for these? Rachel J, or there's only one Rachel here. Did you get either of those Ks? All right, what did you get? 5, that's the midpoint, isn't it? 0, good. Very nice. So I'm guessing that you took the error that we had here and multiplied it by 4 squared, which makes sense because we would say that the error after 4 midpoints should be approximately 1 over 4 squared times this, whatever this is. Now this, you would think, would be the error from a single midpoint, but I've found that the single, oh wait, we don't have that. I guess we have the error right there. I found that the error from a single midpoint or a single Simpson's rule often doesn't quite follow this. It's kind of harder to predict, so that's why I wanted to go to 4. Probably be better to start with 6 or 8, but okay, so that's that. Did anyone get the similar K or number from Simpson's rule that wants to share it? Yeah, what did you get, Alyssa? What was that? 0.43. Notice that that is much closer to our single Simpson's rule. What was it, 3.6? So 4.3, pretty close. This is, once again, just going to be a good guess, but we're going to see how close we are in just a minute. So I want to be within that much of each of these. So I want my error, so maybe I should just write this down to help you out. You probably already did this. So midpoint, we would do this, 0.000, is it 3? I should have put another 0 in there. It's okay. If my Simpson's rule is not as good as I want it to, I'll just throw another 0 in. So I want this to be less than or equal to, you might as well just make it equal because, anyway, let's just set it equal. 1.502 times 1 over n squared. And I want to solve for n squared. So solve for n. So if you haven't done it already, do that. And then for Simpson, we're going to do something similar. 0.43 times 1 over n to the 4th, solve for n. And I think I'm going to be disappointed with Simpson, but what can I do? I don't think I'll be disappointed with midpoint, though. Hmm. All right, let's see what we got. Did anyone do the midpoint? I did Simpson. I'm so obsessed. I wanted to make sure that Simpson was reasonably good. But did anyone do the midpoint? You got it, Alyssa? 123? All right, that sounds reasonable. I'm guessing what you did was you just solved for ins. You just so you divide both sides by 0.0001. What do you get? 15,000 and something, and then do the square root of both sides. It sounds reasonable. Okay, I did this one. I got about 8. It's actually 8.09, but let's see how this compares with actual data or our actual computations. So give me a sec to do this. So let's do this with, I'm going to do the midpoint. So down here, we'll just, well, I'll make a new line. Yeah, the way that I'm doing this is not very efficient, but I don't care. Let's make a new line. And this one, we're going to do Simpson's rule 8 times. And the midpoint rule, what was it, 123 times? 123 times. Let's see how close we are. So there it is, the very last one. Oh, interesting. Oh, this gives me so much joy. Look at that. I was a little concerned that that we wouldn't hit it right on, but look at that. Almost perfect with Simpson's rule. Almost exactly. Now the reason why it's not is because the actual number of iterations should have been 8.1. So I should have rounded up to 9 to get below this. So 8 iterations was so close though. And look at this, 123. I'm guessing that we should have done 124. Or did you round? Oh, sorry. Yeah, wrong person. I knew one of you did it. Very nice. So 124 probably would get us right there. Interesting. That's so beautiful. So there's that. Now, what we're going to be doing on Friday. Well, let's see. Just a minute. First of all, I should explain what you're going to do for homework, and then we'll talk about Friday. So where was this? I feel like it was in the other book. I should have written it down. I think it's 19 and 20. Give me a sec. I didn't write it down. That was my problem. Hold on a sec. So I believe it's in the first book, the tea time. Yeah, 19 and 20. There it is. Okay, so I'll show it to you on the screen. I don't have it up on our website yet. Whoops. Let me pull this over so you can see. And then we'll talk about sort of strategies moving forward. There we go. Okay, so it's 19 and 20. Notice that what it's asking you to do is what we just did, but with a different function. So it's essentially the same thing. They say, we're going to let I be this integral, the value of that definite integral, and you're going to approximate it using one midpoint, basically. I don't really like that. I think that you should do it using maybe 4 midpoints, but whatever. You can do 1. And then you use your answer to this to try to estimate, kind of like what we just did, estimate the number of subintervals. And they tell you what the answer is, what the antiderivative should be, rather the definite integral should be, so that you can compare. And it is the same question, isn't it? 10 to the negative 4, 4 zeros, or did I have 3 zeros? Whatever. And then the same thing for Simpson's rule. So you have those two. And then it says down here to use Octave. We don't use Octave. We use Python. So you're going to use Python to actually calculate those two to make sure, see how close you are in your prediction. So that's interesting. Now, here's the thing, a couple of things. We are being incredibly inefficient. I'll put those homeworks online just in a bit, but that'll be for Friday. So we're being really inefficient here. A couple of reasons. Number one is you'll notice that, let's see, go back up, come on. There it is. Okay, so let me complain about the way we've done things. Number one, every time I call these things, so composite Simpsons, composite midpoint, I'm doing extra work because check it out. I do this work and I do all these function calls. And then down here, I'm doing all the same things again. Couldn't I, and actually I'm saying this sort of rhetorically, couldn't I just take the answer from this and maybe do a little bit of mathemagic with it to get the answer for this? And the answer is yes, it is possible to take the composite Simpsons rule for one Simpsons rule and then take that and then do a little bit of magic, not much, to get the composite Simpsons rule for this. And it's way less work. And in fact, if you keep going, that'll save you a lot of work going down to do 123 of these. The second thing is that it's unnecessary. So even though we've come up with our error estimate, it's not necessary to do quite so many iterations of this thing. I guess I'll explain why on Friday, but one way to think of this is that we want to target our midpoint rules for the places, the problem areas. Here, let me just show you what I mean with a quick function drawing, and then we'll go, sorry. So if you have a function that does this, so over here, it's like, well, that's pretty darn close, that rectangle, but over here, this rectangle might be much further from the truth. So we want to target where we actually make our refinements, if you will. So that'll be on Friday as well. So we'll deal with refining our algorithm and refining our method to try to make it more efficient on Friday. So I'll put the homework online right now.